Uh, Thanks, Ovanis, for organizing this workshop, and thanks everyone for joining. Today, I will be presenting the joint work Nash Equilibria in non-zero-sum differential games with impulse controls. This is a joint work with Vishwanadha Reddy from Indian Institute of Technology, Madras, and George Zaccour from HEC Montreal. The outline of this talk is as follows. First, I will give a motivation for this work. Then I will introduce the general non-zero-sum differential games with impulse controls. Thereafter, I will talk about open loop Nash equilibrium. Finally, briefly, I will mention about feedback Nash equilibrium in linear state differential games. And lastly, I will conclude and present some open questions that exist in this area. So the motivation for this problem is as follows. There is suppose a central bank that announces its interest rates at specific dates during the year, while firms make production and marketing decisions daily. In cybersecurity, an attacker launches its viruses to inflict damage on a system at pre-selected instants of time, while the defender is continuously investing in reducing the system's vulnerability. As you can see, each of the interventions by the central bank or the hacker can cause a jump in the state variable and additional cost to the player. Also, the above two problems can be modeled as finite horizon differential games with one impulse player. However, there is a difference between these two problems. In the central bank example, the central bank states in advance when the interest rate announcement will be made, while in the cybersecurity example, both the timing of impulses and their values are endogenous. Another example that you can think about is regulation, where the government is trying to decide when to put a cap on the pollution levels of a firm while the firm is continuously investing in production levels. And the government has to decide when and how much taxation should be introduced at a particular time. The literature review about impulse control problems is as follows. There are some impulse control problems where the number of jump instants, basically this is just the impulse timings are fixed, or the impulse instants are known a priori. Applications include dike heightening to protect against floods, epidemic control, inventory control, product quality improvement, and many more. Typically, for open loop controls, Pontryagin maximum principle is used, while for feedback solutions, Bensusan-Lyon's quasi-variational inequalities are used. However, in differential games with impulse controls, the literature deals mostly with zero-sum case, where pursuit evasion has been a topic which has received much attention. There is zero-sum differential games with one player using continuous control and the other using impulse control. This problem was studied in a deterministic setting in Yong and in a stochastic setting in Azimzadeh. However, for stochastic impulse games, both players use only impulse controls, and this problem was studied in COSO for the zero-sum case and Aid et al. For non-zero-sum case. Mostly the problems which are being studied here, their assumption is that the controls are of threshold type, more popularly known as SS type control policies. And there are some results for impulse games for where closed form solutions were derived, but only for linear state impulse games. Now I will describe my model, which is a deterministic finite horizon two-player non-zero-sum differential game model where player one uses continuous control while player two uses impulse control. T is less than infinity, and this is the duration of the game. Ut is the control action of player one at time t in 0 to capital T, while U tilde represents the strategy of player one, which is the action profile for all times in 0 to T. Script U is the strategy set of player one. Now, for player two, we introduce impulse controls where Vk determines the impulse level used by player two at time instant tau k, and V tilde, which is a sequence tau 1, V1, tau 2, V2 until tau k, Vk is a strategy of player two. Here, script V represents the strategy set of player two. Also, K, which is the number of impulses, is a decision variable of player two. the model is as follows. In classical differential games, we see.
Sorry, short question. On the previous slide, so you're considering open loop control, right?
Yes.
And it stays open loop, or when there is an impulse action that turns to be closed loop or feedback, no?
No, here I assume that the players know only the initial state, and they determine the controls, their controls throughout 0 to t, depending on the initial state. Yes. So
initial state at the initial time t0, right?
Yes. Yes.
Okay.
Yes. In classical differential games, we see that the state evolves continuously according to the differential equation x dot t is equal to some dynamics, which are continuous dynamics, which are controlled by player who has a continuous control. However, with impulse controls, this equation holds only for those instances where there is no impulse, while at the impulse instant, player 2 controls gives a jump to the state. And this jump is given by this function g, which is a function of x and vi, which is vi is the impulse level of player 2, where the impulse timings are also determined by player 2 and the number of impulses is also determined by player 2. Player 1 uses strategy u tilde to maximize its objective function. However, you can see that here there is a cost g1 at the impulse instant, which you will not see in the classical differential games mostly. Player 2 uses strategy v tilde. Now you can see that there is a continuous payoff that player 2 is receiving due to the control of player 1 and the state, but also there is a fixed cost g2 which is incurred at the impulse instant.
Quick question: is there an a priori upper bound on k, the integer k?
Here we don't introduce, but we consider only finite number of impulses.
But unbounded, it can be any big number.
Yes, here we consider any big number.
Okay.
The assumptions are that we assume the dynamics to be Lipschitz continuous, and the functions f1, f2, g1, g2 are continuous and partial, and there are continuous partial derivatives of all these functions with respect to their arguments. S1 and S2 are continuously differentiable, and the state trajectory is piecewise continuous and is left continuous at points of discontinuity. The action sets are assumed to be compact and convex, and impulse levels with 0 value do not induce a jump in the state. So if there is no impulse, then the state is continuous at that time. And impulse instants are assumed to be interior and separable because of the problems that we are looking at mostly in regulation and cybersecurity. And now we define the Nash equilibrium. The strategy profile u tilde star, v tilde star is the Nash equilibrium of the differential game if the following conditions hold true. Now you fix the strategy of equilibrium strategy of player 2 to be v tilde star, and for all strategies of player 1, u tilde star should maximize the payoff of player 1. Similarly, we can define the equilibrium payoff of player 2 and the equilibrium controls. Here I will be looking at necessary and sufficient conditions for open loop Nash equilibrium. Then we look at we impose some structure on this problem by considering linear quadratic differential games and linear state differential game, and see what results we can obtain. Now, if the strategy profile is a Nash equilibrium, then U star solves the following optimal control problem for player 1, where V tilde star is given, basically the number of impulses and the timing of impulses, as well as the level of impulses is given, and the player 1 solves its optimal control problem. It's a non-classical problem because there is a fixed cost at the impulse instance and there is a jump in state at the impulse instance. Now, the Hamiltonian can be defined for player 1, and we introduce a extended Pontryagin maximum principle for this problem, where U star can be obtained by maximizing the Hamiltonian of player 1, and H1 star denotes the maximized Hamiltonian of player 1. Now for equilibrium control U tilde star, and corresponding state X star, the necessary conditions are that there will exist a co-state trajectory lambda 1t, such that at the jump instance, the equilibrium state experiences a jump equal to the function g, which is determined from the equilibrium timing and state and the controls of player 2. And as you can see here, the co-state of player 1 will also experience a jump due to the gradient, depending on the gradient of the jump with respect to x, as well as the gradient of the cost function of player 1 with respect to x. For
So a very simple follow-up question to what Pradeep was asking before. Is K star here the number of jumps a choice variable, or is it given?
Here it's a choice variable. We need to determine it from our problem.
But here player 1 takes it as given because it's a strategy of player 2. Player 2 will pick K.
Yes, indeed.
Okay.
So at the non-impulse instance, the state trajectory, the continuous evolution is as we know in classical games, but these are apart from the instance where the impulse occurs. Now we introduce the impulse control problem of player 2. Now, given the equilibrium controls of player 1, player 2 solves its impulse control problem where the equilibrium controls of player 1 are known, but player 2 determines the timing and the level and the number of impulses. The Hamiltonian and impulse Hamiltonian of player 2 are defined as follows. This is the continuous Hamiltonian, and at the impulse instant, there is a impulse Hamiltonian of player 2. Now, the Blackier in 1977 provided the optimality conditions for this problem where the equilibrium control of player 2 is obtained by maximizing the impulse Hamiltonian of player 2. And this is the maximized Hamiltonian of player 2. State and co-state experience a jump, which is x dot. At non-impulse instance, the state is continuous, and but at the impulse instant, it experiences a jump, which is given by this function, and the co-states also experience a jump, which is given by this function. However, you can see that here there is one condition missing. Here we need to also determine the impulse instant, and this condition is given.
I'm not seeing. Go back one page.
Yes.
You are saying those conditions will determine the integer k also.
No, these conditions.
But the guy Mr. 2 is choosing k also.
Yeah,
How does he decide which k to pick? And you say that there is no upper bound, so k can be any integer.
I will illustrate how in the linear quadratic case how we obtain the k through the optimization problem.
Okay,
Here we give the necessary conditions which will determine the equilibrium controls of player 1 and 2. And in LQDG case, I will show you how we determine the k. And maybe then it would be great if we can discuss this issue about whether the approach is correct or what other alternatives are. There is one approach that we used for determining k. I will discuss it in the LQDG case.
Okay, but this page takes k as given even for player 2 and tries to find how other things are on this page, page 16.
Here I say that these are necessary conditions. So if you find the equilibrium, then these conditions need to be satisfied.
Okay.
And the Hamiltonian continuity condition will determine the impulse instance for player 2. These are necessary conditions. And we will consider that the equilibrium timing of impulse lies in 0 to t. We will not consider cases at 0 and at capital T. So the optimality conditions for player 1 and player 2 give the candidates for open loop Nash equilibrium of the differential game. Now suppose that there exists u tilde star, v tilde star, lambda 1, lambda 2, such that the necessary conditions are satisfied. Then if the maximized Hamiltonian of player 1 is concave in x, the Hamiltonian of player 2 is concave in x, the salvage values are concave in x, and this function, which is the cost plus co-state multiplied by the jump in state, is concave in x, and the impulse Hamiltonian is jointly concave in xv, then these u tilde star, v tilde star determine the open loop Nash, give the open loop Nash equilibrium of the differential game with impulse controls. Now we specialize this problem to linear quadratic differential game, where the dynamics are linear and in control and in state, and the objective functions of the players are quadratic in state and controls. Here we can have more general cost structures. I have in the paper we have given it in great detail. Here I will consider only this homogeneous model. The necessary conditions follow from the Pontryagin maximum principle for player 1 and player 2, and the dynamics of co-states evolve backwards in time while the state evolves forward in time. Now, what we can do is we can represent the initial conditions through this equation, where yt is compactly written for x co-state of player 1 and co-state of player 2, and we can write the evolution of yt along with the jump in y. Then we can compute the yt at each time instant as a function of the impulse instants. Now, everything is given in terms of impulse instant. These functions phi and where phi are also in terms of impulse instant. Suppose we assume that impulse instants are known. They are tau 1, tau 2, tau n until tau k, fixing some k. Now we determine yt. Now this yt should also satisfy the Hamiltonian continuity condition. This is a system of equations that must hold at impulse instants, and this is given completely by the impulse instant. So it's a highly nonlinear system of equations which can be formulated as a nonlinear optimization problem. Now, for a particular k star value, we can solve this problem, compute the equilibrium payoffs of player 1 and player 2, as well as the open loop equilibrium strategies of the players, which are given by U star and Vi star. We consider this numerical example and use the optimization solver fmincon to solve the ILQDG. Here you can see that we have considered general case where we have interactions between controls and the state as well. So our model can handle even those cases. One approach that we take, which is also used in other papers like Shahim and Neumann, where we look at the equilibrium payoff of player 2, who is only responsible for giving an impulse to this in this problem. It looks at its equilibrium payoffs and determines at what impulse levels this payoff starts decreasing, and it gives an impulse at this level of 5. Now you can argue that, okay, you have not established theoretically that value function indeed is monotonically increasing up to a given number of impulses and then it decreases. Here, this is an assumption because the number of impulses are not unique. So here we have taken this approach to identify the equilibrium number of impulses. Otherwise, it's difficult to compute the equilibrium number of impulses. Hello, do you have any questions or comments?
So I since you don't have a theoretical proof that the best k is bounded, this is sort of almost computer evidence, empirical evidence for the assumption.
Yes, indeed.
Would you agree with that?
Yes, indeed.
Okay.
But I will show that if we introduce more structure, then we can get some results, and that I will introduce now. Now we compute the equilibrium controls, state and co-states, where we see that there is a jump in the controls and the states as well as in the co-states of player 1 and player 2. Now we consider linear state differential games. Can we say something more than what we obtained in linear quadratic?
Sorry, you're a little bit short of time, so maybe 3 or 5 minutes.
Yes, I will finish in 3 minutes, yes. So here the equilibrium number of impulses will be less than equal to 1. We can show theoretically that there will at most be one interior impulse in this linear state differential game model, and that timing of impulse is also obtained in closed form, and the level of impulse is also obtained in closed form, and it depends on player 1's controls, problem parameters, and as well as on the problem parameters of player 2. So here we are able to show uniqueness of equilibrium in linear state case, but establishing it in linear quadratic would be difficult, and computing the number of impulses is difficult problem, and this is one way by which we resolve this problem, as has been done in the literature. Now for feedback Nash equilibrium in linear state case, we know that the open loop equilibrium strategies might not constitute the equilibrium of the subgame. Under the feedback information structure, the player's strategies depend on the current state and time, and they are also strongly time consistent. We already know that in classical linear state differential games without impulse controls, the open loop and feedback Nash equilibrium coincide. Now we can show in our paper that the impulse instants, when they are given exogenously, open loop and feedback Nash equilibrium coincide in scalar non-zero-sum linear state differential games with impulse controls. However, when the impulse instants are endogenously determined, the two equilibrium are different. And finally, for conclusion, in this paper, we provided the necessary and sufficient conditions for open loop, for existence of Nash equilibrium in non-zero-sum differential games. For linear quadratic differential games, we provided an algorithm to compute the equilibrium. Closed form solutions were obtained in linear state case. Some of the extensions for this problem could be sample data Nash equilibrium and feedback Nash equilibrium. Another case could be both players have both types of controls. And lastly, we can consider stochasticity in our model. The preprint of our work can be accessed using the following QR code. And any comments and questions would be greatly appreciated. Thank you very much.
Thank you, thank you. So, anyone else has more questions?
May I ask a question? My question also about K. So when you write the necessary and sufficient conditions, do you assume that K is known for both players, or it is still unknown?
Oh, it's still unknown. These are necessary conditions, yes.
But then you, on slide, on page 25, you have a figure when you choose K. So will it be correct if I say that you say solve you solve the system, find the control and state variables for any given K, then draw this curve and then select K?
Yes, when I'm writing the necessary conditions in the proof, I mean, it can be referred to in the proof, I mean, in the paper. Then I just assume that when I'm deriving the necessary and sufficient conditions, I don't assume that the number of impulses, I mean, what will be the K. But when I'm solving for, because I'm trying to use these necessary conditions to determine the equilibrium number of impulses, then I first fix a K for linear quadratic case in order to determine the K. Yes.
Oh, okay. So if you are saying that K is unknown, right? So it's a decision variable for player 2. So the objective function like J2, right? So there is a term in this function. The sum and the number of summands is unknown, right?
Yes.
So how can you be sure that this like sum is bounded, say?
Okay, I assume a fixed number of impulses, but those number is unknown. I mean,
so number of impulses is fixed. So
yes.
it is unknown but fixed.
Yes, it's actually I am saying that the K is less than infinity. I am just saying that K is
and for any K you will have a unique, and you will have unique of the system, like the system of differential equations and the continuity of the solution, right?
In the linear state case, we can show that that there is a unique solution, and yes, under a finite number of impulses, we can show that the state dynamics is unique. Yes, so that follows from the Lipschitz continuity.
Mm-hmm.
Of the
Okay.
state.
Thanks.
Thank you. Thank you for your comment.
Okay, so